thanks for the invitation and thanks for coming. So this is going to be joint work with Thomas Lamb, and there's two papers, very recent on the archive. They almost the same names, but totally separate papers. And the talk is going to involve a bunch of objects. I'm going to assume people are familiar with knots, so I'm going to start with the Positroids part. And please feel free to stop me if you have any questions. So Positroids live inside the Grassmannian. The Grassmannian is the Grassmannian Kn over some field, let's say complex numbers, is the set of all linear k-dimensional subspaces of C to the n. And if you pick a basis, then you're gonna get a k by n matrix, right? So you can alternatively represent it by the set of full rank k by n matrices. But if you choose a different basis, you are going to get a different matrix, which is going to be related by the original one by row operations. So so that's some nice projective variety, and inside of it there's going to be the Positroid variety, which is going to be the main geometric object of this talk. So by the way, I'm going to scroll the right-hand side quickly, and the left-hand side is going to be, it's going to contain the same information, but it's going to be scrolled much slower. So feel free to refer to the previous formulas on the left. So yeah, here's the definition of the top dimensional open Positroid variety, which so what you do is you just take the it's an open subset of the Grassmannian, which consists of you take all matrices such that certain maximal minors have to be non-zero. Namely, the cyclically consecutive minors have to be non-zero. Delta 1, 2, all the way up to k of v is non-zero. Delta 2, 3 up to k plus 1 of v is non-zero, and etc. all the way up to delta n 1 k minus 1 of v is non-zero. So there is n inequalities, and so you just remove these kind of hypersurfaces, and what you get is this open Positroid variety. And yeah, maybe I should give an example. Let's say I give an example for k equals to 2 and n equals to 4. So that's the smallest non-trivial one. And in this case, what happens is, well, so let's see, what should I do? I should take k by n matrices. So I'm taking 2 by 4 matrices, and then because the first k columns are going to be non-zero, that means I can apply my row operations uniquely to kind of force the first k columns to be the identity matrix. And then the remaining entries are going to be just some numbers, a, b, c, d, and the conditions are going to be given by the remaining minors being non-zero. So for example, if I take the second and third column, then the determinant is negative a. So a has to be non-zero. And if I take the last two columns, then the determinant is AD minus BC, has to be non-zero. And then there's one more, which is kind of wraps around. So D has to be non-zero. And that's it. That's your space. You know, it's always an affine variety. You remove some polynomial hypersurfaces from it. And the two questions that I'm going to try to answer today, well, in the first part of the talk, are going to be about the algebra and geometry of such a space. So the first question is, well, this is defined over an arbitrary field, so I can choose my field to be the finite field with q elements, and then this whole thing becomes a finite set. So the question is, how many points in that finite set? That's the first question, and the second one is what is the Poincare polynomial of this space when considered as a complex manifold. So over C, it's a smooth manifold. It's non-compact, but still I can talk about beta numbers. So what's the Poincare polynomial? And yeah, so these are the two starting questions. And by the way, for the Grassmannian, if I take the Grassmannian instead of the top Positroid variety, I can ask the same two questions, and it turns out that they both have the same answer. Both answers are given by what is called the Q binomial coefficient, which, so by definition, it is given in terms of some ratio of Q factorials. Q factorial of n, Q factorial of k, Q factorial of n minus k, where the Q factorials are defined over here. And if you want an actual combinatorial definition, because here it's not clear that this is the ratio is going to be an actual polynomial, but it is going to, yeah, the numerator is divisible by the denominator, and the ratio turns out to be the combinatorial sum over all Young diagrams that fit inside a k by n minus k rectangle of q to the number of boxes of lambda, which, so this whole stuff for the Grassmannian follows from the Schubert decomposition. To me, I'm not going to go into that because there is no Schubert decomposition of the Positroid varieties. But yeah, so now I'm going to try to answer these questions for the Positroid variety. And what's going to happen is that I'm going to have to introduce Catalan numbers. Definition. And I'm going to go slightly more general. I'm going to talk about rational Catalan numbers, which, so the setup is that you fix two integers, a and b, two positive integers, and you assume that they are coprime. Then by definition, the rational Catalan number is given by 1 over a plus b times the binomial coefficient, which is divisible whenever the GCT is 1. And again, there is a combinatorial interpretation which comes in terms of lattice paths. So it's the number of Dicke paths inside an a by b rectangle. So what you do is you you draw an a by b rectangle, maybe something like this, and then you draw the main diagonal. So this set of Dicke paths, it contains all lattice paths that go up and right and never touch the diagonal. And because of this GCD condition, there's no lattice points on the diagonal, so this is a well-defined notion. All right. Yeah. If you have any questions, let me know. If not, I'm gonna start explaining the main result. Well, the first incarnation of the main result. So, which answers the two questions above. Right. So the first, I'm going to start with the point count, which is given by, so I'm going to assume that the GCD of k and n is equal to 1 for now. Later, I'm going to do this more generally. But if the GCD is 1, then the number of points over a finite field is given by q minus 1 to the n minus 1 times, let me denote it by c prime k n minus k, where, so of q. So this guy is going to be the q analog of of the rational Catalan number. So CAB of Q prime, by definition, is given by what I do is instead of taking the, so here's the definition of the Q binomial coefficient, and then I'm gonna, to get the definition of the rational Catalan number, I would just replace every number by its Q analog. So I would get something like 1 over the Q analog of A plus B times the Q binomial coefficient, A plus B, choose A, and it's also going to be divisible, so it's all good. And turns out that that's the point count, just the Q analog of the rational Catalan number. And what about the Poincare polynomial? Well, so let me denote it by P of pi kn of Q. That it turns out that is given by another Q analog which is different from the first one. So it's times C double prime K n minus K of Q, where the second Q analog C double prime AB of Q, and here I'm going to take the second, the combinatorial definition, and generalize it to, well, restrict it to Dick paths. So it's going to be some combinatorial sum over all Dick paths of Q to the area of P, where area is some statistic. It's like, the area is like the number of boxes which are fully contained between your Dick path and the diagonal. So that's it. That's the answer to both of these questions. And by the way, while I'm here, let me mention a nice corollary of the first of the point count result. So corollary, which is obtained by basically, you know how many points in a Positroid variety, some Q analogs, and you know how many points in the Grossmannian, also some Q analogs, so you can divide one by the other. And after you divide, you get, everything cancels out, and what you get is the nice probabilistic interpretation, that the probability that a uniformly random k-dimensional subspace of C of Fq to the n belongs to the top Positroid variety is just equal to Q minus 1 to the n over Q to the n minus 1. And what is weird about this corollary is that the right-hand side does not depend on k. So k is the dimension of your vector of your k-dimensional subspace. So it looks like the left-hand side should depend on k, but it turns out to not depend on k. And we have no explanation for this. I mean, we know the proof. It comes out of knot theory, but without knot theory, we don't know how to explain this statement. Anyway, that's the kind of introductory part. And what I want to try to do next is to find a common generalization. So these two results are sort of similar but different. So I want some result which implies both of these statements at the same time. So the goal is to find a common generalization. Yeah. And so the way to do this is I'm going to do it side by side. So I start with the left-hand side. And well, here there is something called the mixed Hodge polynomial. So if you take let's say you take work over C and you take the cohomology of your open Positroid variety, then it is a graded, it has a single graded vector space, or even a ring, but definitely a vector space. But actually, if you, it is secretly a bigraded vector space. So if you take the ith cohomology, then it splits. There is a canonical splitting as a direct product over all integers p, hi p comma p of pi kn. That's called the Deligne splitting. So I'm not going to define it, but it's some canonical construction. It is factorial. If you have a long exact sequence, then it's going to respect your long exact sequence, and etc. So actually this guy is not a graded, but it's a bigraded vector space. In particular, you can write down the corresponding like Poincare polynomial, which is going to be in 2 variables. And I'm going to call this polynomial the mixed Hodge polynomial. Mixed Hodge polynomial, which I'm going to denote by the same letter, p of pi kn, but it's going to depend now on q and t. And it's going to be not quite a polynomial. It's gonna be a polynomial in q to the 1/2 and t to the 1/2. There's some normalization, and the idea is that integer powers are going to correspond to even homology, and half integer powers are going to correspond to odd homology. So if you get an honest polynomial, that means the odd cohomology vanishes. Okay, that's the left-hand side, and the right-hand side is given by, there is something called the QtCatalan number, which comes from Macdonald theory. So, well, rational QtCatalan number, which is, so it can be defined in several different ways. And, well, my favorite way is to do this combinatorially. So it's just some very explicit sum over dig paths of q to the area as before times t to the dinv of p. And this dinv is the number of diagonal inversions. It's some combinatorial statistic, counts some number of pairs of steps. And it's unimportant for this talk. What exactly is that? It's just that you define such a Qt polynomial. And that's it. That now I can state the common generalization. So yeah, by the way, the QtCatalan numbers were introduced by Garcia-Hyman in '96 for the case of when b is equal to a plus 1. That's the usual Catalan, usual, not the rational Catalan number. And then the rational version was introduced by Lauren Warrington in 2009. And yeah, so, and this guy specializes to both of the 2 Q analogs I gave above. So so now here is the actual first main result. Assume that the GCD k and n is equal to 1. Then the claim is that the mixed Hodge polynomial q and t is equal up to a stupid factor. It's equal n minus 1 to the qt k n minus k to the QtCatalan number. So yeah, that's the main result. And before I go into details on like the proof and generalizations, let me try to explain the consequences from the combinatorial perspective, which are hard, very hard to do explicitly combinatorially. So the corollary for the QtCatalan numbers is that the QtCatalan numbers are Qt symmetric and Qt unimodal. So some sequence of coefficients increases and then decreases and is palindromic. And so the symmetry property is known. So it follows from the rational shuffle conjecture. But the unimodality part is a new result, doesn't follow from the literature. And the reason it follows from this statement is that for the left-hand side there is more structure. So there is something called the both of these properties follow from the curious Lefschetz property for cluster varieties. So cluster varieties come from cluster algebras, and so the idea is that if you look at these two papers over here, Lam Spire 2016 and our paper with Thomas from 2019, then the first paper proves that if you have a cluster variety, then there is the curious Lefschetz property. So you get Qt symmetric and unimodal polynomials. But then you have to show that your Positroid variety is a cluster variety. And yeah, for the top Positroid, this was done by Scott in 2006. But for arbitrary Positroids, this was done in this paper. And definitely one of the applications we had in mind was to have this Qt symmetry and unimodality for all Positroids. So yeah, that's the end of the first part. I guess now I'm going to talk about arbitrary Positroid varieties. If you have any questions, let me know. Yeah, in the cluster algebra there is something called the GSV form. So if you talk about Drum cohomology, then yeah, there is a 2 form which you write down. It exists for any cluster algebra. And just in terms of the quiver, you can write it down, and it's mutation invariant, and this guy gives you the Lefschetz operator. Yeah, you can. Well, you can write it in terms of coordinates on the Grassmannian, but you have to use the quiver, like the Playvig graphs. You have to use them in some way. I don't know if it can be written without referring to any Playvig graph. Yeah, thanks. I'm not sure. I mean, you can just subtract the point count for the whole thing, and you can know the point count after you subtract. So you can. Yeah. Anyways, the short answer is I don't know, but we do give point counts for all Positroid varieties, so you can sum them up. All right, arbitrary Positroid varieties, and so. Since this is a knot theory seminar, I'd like to actually, these are not usually defined in talks, so I'd like to take this chance to explain the definition, because I think these are pretty nice objects. So I'm working inside of the Grassmannian with the matrix definition. So let's say I have a matrix, some k by n matrix M, and it has, let me denote its columns by M1, M2, all the way up to Mn. And then what I'm going to do is I'm going to extend this periodically to all. So I want my columns to be labeled by integers. And just in an n periodic way. So I want mi plus n to be equal to mi for all integers I. 1, 2, up to n plus 1, to 2n, and etc. So, and now to any such full rank k by n matrix, I'm going to associate a map, which I'm going to denote f sub m. It's going to be a map from bracket n to bracket n, where by bracket n I just mean integers between 1 and n. So how do I define this map? Well, let's see. I want to define f sub m of I. I'm going to define it in terms of these columns of m. And the definition is that I take the minimal j greater than or equal to I, such that mi belongs to the span of mi plus 1, etc. up to m sub j. Right. So maybe I should try some example. Yeah. So maybe you choose some column mi, and then you just scan to the right. So if the next column is parallel to mi, then j is I plus 1. Or if it's not parallel, you keep scanning until you find some j such that these consecutive columns, their span contains mi. And then you set f of f sub m of I to be equal to j, except that you have to, I want the target to be bracket n, so I just take it modulo n. Oops. Modulo n. And so that's it. That's the definition of how I assign a map f sub m to every matrix m. And it turns out that f sub m is a bijection. So it's a permutation for any full rank matrix M. This is a permutation which this permutation only depends on the row span of your matrix. Right? So if you apply row operations, then these conditions don't really change anything. So so you can now define a Positroid variety given a permutation f in Sn. You can define the open Positroid variety by just taking all elements in the Grossmanian such that the corresponding permutation is equal to f. And so that's the definition of an arbitrary open Positroid variety. It is due to Knudsen, Lam, and Spire. And one disclaimer I have to mention is that this only works if your permutation has no fixed points. If it has fixed points, then it's slightly more technical, but the idea is still the same. So if you take matrices satisfying some rank conditions on consecutive intervals of columns. And in particular, if you look at this definition closely and try to relate it to what I said at the beginning, right? I defined one top-dimensional open Positroid variety. Then you can see that the way to get there is to set for a specific permutation fkn in Sn given by fkn of I is equal to I plus k modulo n. For this permutation, the condition you get is just that any k cyclically consecutive columns should be linearly independent. So your open Positroid variety fkn is just equal to the one I defined previously. So in particular, what I'm going to try to focus next is I'm going to try to generalize the original result for the top Positroid variety to arbitrary Positroid varieties. So the next question is, what is the mixed Hodge polynomial of an arbitrary Positroid variety? And well, the answer here is going to be given in terms of knots and links associated to Positroid varieties. So let me try to explain how to associate a Positroid link, how to associate a link to any permutation, basically. And the construction I'm going to explain is actually not written down anywhere so far, but we think it works. So, and it's very simple. So I'd like to, so let's say I'd like to define a map which takes a permutation and outputs a link beta hat sub f. That's called the Positroid link of f. And so here's what you're going to do. You take a circle and you draw you draw the numbers from 1 up to n on the circle. And then you draw your strands. So f is a permutation. Maybe it sends 1 to 4, 4 to 7, 7 to 2, 2 to 5, 5 to 6, and 6 to 1, maybe something like this. And maybe it also sends 3 to itself, even though that's not allowed. Yeah, anyways, you get some diagram like this. And this looks like a link diagram, except that I have to tell you which crossings are over crossings and which are under crossings. So the recipe is very simple. So if you have a strand from A to B, if the strand crosses another strand C to D, then A to B is above if and only if B is less than D. So whichever strand has the smaller target is above everybody else. So in this picture, the strand that terminates at 1 has to be above everybody, and then the strand that terminates at 2 above everybody else, then 3, and then 4, and then 5, and that's it. And you get a planar diagram of a link, and that's called the Positroid link associated to your permutation. Very simple. And the way to get this construction, you can deduce it after some work from these two papers, Fomin, Pilavsky, Shustin, Thurston, and Shanda, Truman, Williams, Zaslow, which associate links to Playbig graphs, which are some planar bipartite graphs. And yeah, after some work, you can get to here. And so now I guess one last piece I have to discuss is the torus action. No, this is not a positive knot. Well, yeah, this particular one is positive, but for some permutations you're going to get you're not always going to get positive knots. Okay, so the torus action. You have, let's say you take the group T of, it's the group of diagonal n by n matrices, invertible, determinant 1. Then this group acts on each open Positroid variety by column rescaling. And so I'd like to take the quotient. Of course, I'm only allowed to take the quotient when the action is free. So the simple lemma gives you a criterion. The following conditions are equivalent. The first one is that the T action is free on the open Positroid variety. The second condition is that the number of cycles of your permutation is equal to 1. So C is the number of cycles. And the third condition is that, well, which is very easy to see to be equivalent to the second one, is that the corresponding Positroid link is a knot. So yeah, and in particular, In particular, when you take the top dimensional open Positroid variety, then the number of cycles of fkn is equal to the GCD k and n. So that's where the GCD condition comes in the previous main results. And also, also if the torus acts freely on your space, then you can take the quotient and the mixed Hodge polynomial behaves nicely. So after you take the quotient, Qt, well, let's say before you take the quotient, they differ by a stupid factor. n-1 times the mixed Hodge polynomial of the torus quotient So now I think I'm ready. Well, okay, let me now talk about knot invariants. So let me denote by p kr of a knot or a link a q t be the triply graded Havanov-Rosansky link invariant. So that's the polynomial that encodes the triply graded dimensions of the HHH of the Rukia complex. So now I can actually state the even more general result for arbitrary positroids. Well, I'm still going to assume that the action is free. So I assume that the number of cycles is equal to 1. Then the claim is that the mixed Hodge polynomial of f, torus quotient of the Positroid variety, is equal to the, let me, pkr top of the Positroid link qt, where pkr top is the top a degree of the Havanov-Rosansky link invariant. Well, top a degree coefficient, sorry. Top a degree coefficient of this triply graded polynomial. So that is yet another main result of this talk. Each next one is more general than the previous one. And so I'd like to, I guess, say a few words about the proof. Okay, I'm probably going to be out of time before. Yeah, okay, let me mention the proof. And yeah, and for the proof I'm going to need even more general. Let me mention the most general result, which I guess is going to be not as accessible as I previously did. The most general result involves Richardson varieties. So what you do is you take any two permutations or any two elements of a finite Weil group, and then you can define the Richardson variety, the open Richardson variety, as the intersection of the Schubert cell for W with the opposite Schubert cell for V inside the flag variety. And so that is some variety which is more general than the Positroid varieties. So namely, for any permutation F, there exists a pair of permutations V and W in Sn such that the Positroid variety is isomorphic to the corresponding Richardson variety, where the isomorphism comes from the projection from the flag variety to the Grassmannian. And the extra property here is that as a permutation, F factors as W times V inverse. So by the way, this Richardson variety is non-empty, if and only if v is less than or equal to w in the Brouwer order. So that's going to be my run-in assumption. And yeah, so these things generalize Positroid varieties, and you can associate a Richardson, what we call a Richardson braid, to each pair v comma w, satisfying this assumption here. So it's denoted b beta vw, and just by definition it is the positive braid lift of w times the inverse of the positive braid lift for v. So this guy is the positive braid lift. And in particular, we claim that in the situation where your Richardson variety is equal to a Positroid variety, then what you get is that the Positroid link I described above is isotopic to the closure of the Richardson link. So the two definitions are, even though they're different, they actually give you the same result. And so now the most general result is actually of the following form. So yeah, there's going to be no more general results than this one in this talk. For any v less than or equal to w inside some finite type while group, the claim is that the HHH0 of the Rouquier complex of the corresponding braid is isomorphic as a bigraded R module to the torus equivariant cohomology of the Richardson variety with compact supports. Yeah, where the FVW is, by definition, you just take the usual Rouquier complex for W and times the whatever dual or inverse one for V. These are just Rouquier complexes which were discussed by Eugene in the first couple of lectures of the seminar. So that's the main result. And okay, let me if you want to know the proof, you can ask me later. Now I'm gonna skip the proof. There is a proof sketch over here which I'm gonna skip, and instead I'm gonna go back to combinatorics and discuss the Q equals T equals 1 specialization, which was obtained in our very recent paper with Thomas, because we decided to just go back to combinatorics. No Q, no T, just so the assumption here is that I'm going to start with a permutation, and I'm going to assume that the number of cycles is equal to 1, and any such object, any such long cycle gives me a polynomial, right? The mixed Hodge polynomial of the torus quotient, which depends on Q and T. In particular, I can set Q and T to be equal to 1, and I get a positive integer, which in the special case, it gives me rational Catalan numbers. By the way, this result, when for the top Positroid variety, this knot here is going to be the Torus knot, or in general the Torus link, and in this case the HHH was computed by Mellit, and Hogenkamp Mellit. So that's where the QtCatalan numbers come from in our proof. Yeah. And so in general, you get a family of polynomials labeled by permutations. So it is natural to try and study them there, let's say even the Q equals T equals 1 specialization. And so that's what I'm going to try to explain now. So first of all, any such permutation, as I said, gives me an open Positroid variety which lives inside Grossmanian k, n. And here n, which I'm going to also denote by n of f, is just the number of letters. You have permutation on n letters. But what is k? If you give me permutation, I'm supposed to, there's not going to be one in every gross minor, there's just going to be a single open Positroid variety, so k should be uniquely determined by f. So the way this works is, let me try to show you a picture. A picture of how you determine k. Well, first of all, I can write down the actual definition. So k of f is, by definition, is the number of indices I such that f of I is less than I. But the definition I prefer is the following one. You start with your permutation f on the left, which sends 0 to 2, 1 to 0, and etc. The index is labeled from 0 to n minus 1. Now, to that data, I'm going to associate a map f tilde, which is going to send integers to integers. And the way it is defined is, first of all, f tilde of I should be equal to f of I modulo n, and also it should be n periodic, f of I plus n, and also it should be bounded. F tilde of I should be between I and I plus n. So let's see. F sends 0 to 2, so f tilde sends 0 to 2. Now f sends 1 to 0, which is less than 1. So to satisfy this condition, I have to send 1 to 0 plus n, and etc. 2 goes to 3, 2 goes to 3. And 3 goes to, anyway, 5 goes to 1, 5 goes to 1 plus n. So this object on the right is called a bounded affine permutation. It contains the same information, but in a different sort of presentation. Yes, thank you. Yeah, that's actually, that is true, right? So in the matrix definition I had here, when I define f sub m, I take it modulo n. Without that modulo n, I would have constructed the f tilde permutation, the bounded affine permutation. So yeah, that's and this is another presentation, and it's useful. So first of all, k of f is now very easy to see from this picture on the right. Namely, it is just what I do is I can draw any vertical line between two adjacent numbers, and I count how many strands intersect my vertical line, and that's k. And no matter where you draw the vertical line, the number of intersections is always going to be exactly the same. So in this case, k of f is equal to 3, because there is 3 intersections, and n of f is equal to 7, because there's 7 letters. And let me also introduce gamma of f, which by definition is a pair of integers. So it's k of f, comma, n of f minus k of f. So in this case, gamma of f is equal to 3, 4. Yeah. So that's one information that's useful from the picture on the right-hand side, and another piece of information is the inversions. So I'm going to introduce affine inversions, and the reason is that I want to explain what is the dimension. What is the dimension of the open Positroid variety? And it turns out, well, the codimension turns out to be equal to the number of inversions. So here's the definition. You take affine inversion, well, you take inversions of f tilde to be just the length in the Coxeter group. So in other words, it's the number of pairs I less than j, such that f tilde of I is bigger than f tilde of j. And well, so far there's infinitely many such pairs, because it's all n periodic. So I want to count them modulo n. So the extra condition, I can, for example, ask that I belongs to bracket n. So that's it. These are the affine inversions. And for the example I have here, let's see, there's 1, 2, 3, 4, 5, and there should be, and 6. So the length of f tilde is equal to 6. Because I only count crossings modulo n, yeah. And the dimension of the corresponding positroid variety is the dimension of the Grassmannian minus this affine number of affine inversions. So yeah, that's the. And what I'm gonna do now is I'm gonna try to. The goal is I'm gonna try to take my permutation, which is a single cycle, and I want to associate a multiset denoted by gamma of f. It's a multiset of points inside of lattice points inside the k by n minus k rectangle. So the idea is that I take an inversion, and yeah, maybe I should draw another picture. Here's another picture. So you start with some f, right? Or f tilde bounded affine permutation, and you look at the inversions. Here I have 2 inversions. So what I'm going to do for each inversion, I'm going to uncross. So I'm going to resolve the corresponding crossing. My original f was a single cycle. If I resolve one crossing, I get. So let's see. If I resolve this crossing, I get something that has 2 cycles. Right? It's modulo n. It's a product of 2 cycles. And if my inversion was ij, then one cycle is going to go through I, and the other one is going to go through j. So I'm only going to be interested in the cycle that goes through I. When it goes through I, and I'm going to denote it by f1 ij is the cycle through I when I swap the values f of I and f of j. So I multiply it by transposition, and then I get 2 cycles, and I only take the one through I. And then for that cycle, I take gamma of that cycle. So because it uses 5 letters, the sum of these numbers is equal to 5. And because if you draw any vertical line, then it intersects exactly 2 strands, 2 red strands. That's why the first coordinate is 2. And similarly, that's the first inversion. And for the second inversion, I can do the same procedure, and I get the red cycle only uses 2 letters, 1 and 5. And if I draw any vertical line, then the red strand intersects exactly once. So gamma is 1, 1. Yeah. And finally, the capital gamma of f is just the set of all, it's the multiset of all these points that I get from all inversions. So in this case, there was 2 inversions, and the 2 points I got was 1, 1 and 2, 3, where I'm using some sort of matrix notation. So, and notice that in this case, the two inversions gave me 2 different points. In general, there could be repetitions in this multiset. So let me capture the situation where there is no repetitions. So f is called repetition free if the multiset gamma of f has no repeated elements. Yeah. So this sounds like a unnatural definition, but it turns out to be very, very nice and very it defines a very nice class of knots and permutations and etc. So if you try to think about it, like what do these, let's say you take gamma that's repetition free, how does it look like? If you try to picture that, I mean, some subset of the rectangle, but how? What's the picture? So here is the picture. That's an example when k equals to 4 and n equals to 8. And you can disregard the red area for now. So each gamma, these are all possible gammas, and each comes from many different repetition-free f's. And so let me try to state the final result of the second paper. So let me say that denote by gamma hat the union of gamma and 0, 0, k, n minus k. These are the two vertices of the rectangle. And then let me say that gamma is convex if gamma hat contains all lattice points of its convex hull, just like in all these pictures here. Then the theorem, which is in our most recent paper, is that first of all, if f is repetition free, then gamma of f is convex and centrally symmetric, just like in all these pictures. Centrally symmetric means if I rotate my rectangle by 180 degrees, I get the same set. The second claim is that any convex centrally symmetric set gamma subset of the k by n rectangle arises this way. So the repetition-free condition gives you precisely convex subsets. And the third and final statement is that if f is repetition-free, then the specialization of the mixed Hodge polynomial q equals to t equals to 1 counts the number of Dick paths which avoid gamma of f. So in other words, that generalization of Catalan numbers that we get is you kind of take any convex curve and you take Dick paths which are above that convex curve. That just naturally, this notion of repetition-free permutations naturally spits out such Dick paths. And yeah, I guess I'm out of time. So there is a conjecture. There is a conjectural interpretation for the whole polynomial without specializing. In this paper, GHSR 20, where they define generalized Catalan numbers which come from Coxeter links. And so yeah, you can check on the computer that the two polynomials appear to be the same. And finally, there's one more paper, BHMPS 21, which sort of gives a symmetric function which includes these generalized QtCatalan numbers as just a single coefficient, and they conjecture that it's their function is sure positive if and only if the shape is convex. So they sort of arrive to exactly the same objects, but from completely different setup. And that's it. So thank you very much for joining the talk. Yes. Not obvious. No. in the diagram in the circle, the inversions of f tilde correspond to alignments, which are pictures of the form of this type. So whenever you have two arrows which are sort of parallel in the circle, then that would give you an affine inversion. Sort of, yeah. No, we don't know how to do that. Well, well, one comment is that if you draw your link not in the plane but in a thick torus, then there is something called the Fiedler invariant, which actually sort of generalizes our set gamma of f. So you can, there is some speculation that maybe if this guy is repetition free for an arbitrary link in the torus, then probably the Qt polynomial is gonna, well, there's gonna be no odd homology, let's say. But we don't know how to check this because knot homology is tricky to compute in general. Well, it's so no, it's actually, well, it's essentially a multiset. It's a formal combination of homology cycles in the torus, which is the same thing as a multiset of pairs of integers. For the characterization, it's not clear. For the they have some nice structure in terms of let's say if you have a crossing something like this, and if the between 7 and 0, let's say, and the two strands coming into 7 and 0 don't cross, then you can move this crossing. You can move crossings on the cylinder. You can conjugate by simple transpositions, and it turns out that conjecturally, gamma is basically the only invariant of that operation. So if you apply, you can relate any two repetition-free f's to each other by just this simple operation. And so that's one kind of start. Yeah, they have some rigid structure, and we also looked at the quivers. And I don't remember what was the conclusion. Yeah, you can get lots of like exponential or super exponentially many different f's. You get very few gammas, but very many f's. And and we couldn't even prove that they are all related by these simple moves, but the computer says they are. And the link, by the way, it conjecturally or not, I don't remember. If you can take different k and n, and you get different gammas inside different rectangles. But conjecturally, the actual link depends only on the Young diagram. Well, I mean, not even conjecturally. That follows from the interpretation of the knots in terms of this paper here. But yeah, anyways, the point is that the Young diagram above gamma gives you some invariant which is the same for positroids and different Grassmannians, and somehow the properties of the positroid variety are captured by this Young diagram here, surprisingly. Oh, right, yeah, I forgot to mention, yes, the Grassmannian is the disjoint union of all positroid varieties. Yeah. Right, if you take the sum of all, by the way, the point count in general of any positroid variety over Fq, it is a specialization of the Humphrey polynomial. You don't have to take the full Hovanov-Rosansky homology. You can compute it in terms of the coefficient of the Humphrey polynomial. And so in particular, yes, if you sum all these things together, you get the Q binomial coefficient. But we don't have, yeah, it's some identity. I don't know if it, yeah, that's a very interesting question. I have no idea. Even in terms of combinatorics, I don't know, but in knot theory, that's also, yeah, I never thought of that interpretation. Oh, yeah, for the usual Catalan, for the Q equals T equals to 1 specialization, if F is a product of cycles, C1, C2, etc., up to CR, then the Catalan number, the Catalan number for F is the product of the, well, maybe I should use a different letter for the cycles. Maybe G1, G2, GR. These are single cycles. Then the Catalan number for F, which by definition is the Q equals T equals 1 specialization, is the product of the Catalan numbers of GI. So if your permutation factors as a product of cycles, then the corresponding QtCatalan number factor at Q equals T equals 1, it factors as a product of individual QtCatalan numbers. But even if you just allow Q, even if you set only T equals to 1, then we have no idea what's going to happen. It does not factor for Q or Qt. It does not factor. Is that a question or? Well, yeah, you get right. So you get some link invariant, which the links could be tangled together. So it's right, but and yet the number factors through. I don't. This is not known for Hovanov-Rosansky homology, right? The analogous statement. Okay. 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 One of the gradings? Which one? The Q gradient. Oh, okay. That's interesting. That you're so what you're saying is the Poincare polynomial factors. Okay. Yeah. All right. All right. Well, yes, that form I guess is the only interesting class I know. There is, is there a paper? Yeah. Anyways, there are some papers about the compactified Jacobian which have generators in them, like Oblomkov-Yun, I think. And yeah, from the cluster perspective, it's not clear. Apart from the GSV form, it's not clear what the generator should be. There's also the amplitohedron form, which is like the top dimensional form, but I mean, yeah. Anyways, my official answer is that I don't know.